Hello. Hello, Pika. Hello, Nookus. Hey, JP. Hello, Liam. Inze, Mike. D. Stratus, good morning. Did you know that there's a company known as Estes Rockets? They sell model rockets. I have heard of them, and I remember my dad, when he was growing up, he would play with Estes Rockets. Totally unrelated to me. Hello, Belkit. Hello, Benny. Haha. There's also like an Estes Trucks company. I'm also totally unrelated. Hi, Casper. Hump day. Yeah, it's Wednesday. It's hump day. Once we get past this day, it's all just downhill, an easy slide into the weekend. I'm sure. Hey, good afternoon, chat. Good afternoon, everyone. Ando says, I saw a rabbit today. Now, how old was this rabbit? And did you befriend it? Hello, Amin. I saw rabbit tracks the other day. Of course you befriended it. I mean, who wouldn't? Good grief. Ashish saw a reindeer a few days back. A Christmas reindeer. A flying reindeer. I don't know if I've ever seen a reindeer. Liam says, off topic, Dr. E, what is your 1 rep max bench press? Well, you know, COVID and all that. And I haven't really been putting it up. But I would say back in the day, a little bit over 225, maybe? Maybe 250, maybe? Like, not crazy. So I have a younger brother, Nathan, who's just a tank. I think he could put up like 5 Hondo. Formula Q1 says, hey, Dr. E. Hey, Formula. 9,000 pounds? No. Not quite. Brandon says, hey, Dr. E, didn't know you played chess. I'll play you if you have time someday. Maybe at the end of today's class. I'm not very good, so I have to, I just have to tell you that. Link says, guest professor Nathan Estes. We should bring in Big Nath. Maybe he'll come here sometime. I appreciate all the lectures being on YouTube so I could download them and watch them on the plane home. Great. Perfect, JP. We'll keep putting those up. When will we have all the information we need to finish the homework, says Jack. By the end of today, you're going to have everything. All of the keys to the castle will be yours. All right, let's get into it. You're going to have everything. Let's see here. Hello, Not Prof. If you guys don't know Not Prof, he's a professor here at UB teaching math. We're gonna get the key to Zelda today. Yes, I played a little Zelda yesterday. All right, all right, all right. Here we go. We're getting started here. So let's get in some basics. To implement a control system on a computer, this could be like an Arduino, whatever. We will use difference equations. Now, back on either the first or second lecture of this class, I showed you a line of code from that balancing robot. And it writes out the definition of the control law, and lo and behold, that is a difference equation. All right, and so difference equations, you've seen them before in different classes, different contexts. So difference equations describe the dynamics of a system in snapshots. And this is appropriate for computers because we gather sensor measurements at discrete points in time, and we also send commands to any actuators at discrete points in time. And so because we're sending commands in this way, it makes sense that we're going to try to model the systems that we control in that same way. Describe the dynamics of a system in snapshots. This shows how discrete moments from the past and the present affect the future. That's how we're using difference equations. So, just a quick example. Last class, we looked at a simple model of rabbit reproduction. This is Fibonacci's model. Notprof says time is a flat circle. Does that mean it's just a cycle? And this was the difference equation. The population of rabbits at the end of month K is the sum of populations from the prior 2 months. So contained in that equation is the 3 rules of rabbit reproduction, at least according to Fibonacci, that rabbits never die, they reproduce every month. The new rabbits grow up in a month and then they reproduce. So that difference in equation encapsulates all of that. And if you simulate it, like if you calculate the population at the end of each month as a function of the month K, it started at 2 for the first couple months, and then it just like explodes from there. And I think at the end of 2 years, you have like 150,000 rabbits. So it's, we would call this an unstable system. Now, the way that you can check if a difference equation is unstable, you need to take a look at the characteristic equation. And we talked about how to get the characteristic equation for a difference equation. Once you have the characteristic equation, calculate the roots. In order for a difference equation to be stable, all roots must have magnitude less than 1. Less than 1. And the easiest way to remember this, I think, is imagine the complex plane, because roots in general can be complex, like they have real and imaginary components. In fact, we're going to look at oscillatory difference equations today, and these have complex roots. All right, so in general, you're going to find roots with real and imaginary parts. So let's just draw a pair of complex conjugate roots here. If this system is going to be stable, each of these roots has to have magnitude less than 1. And geometrically, what that means is, so the magnitude is going to be the distance of the root from the origin. So it'd be less than plus or minus 1. Well, no, because magnitude is always going to be positive. Magnitude is always positive. So if you imagine a circle, I know that's a little oblong. The root, that circle, if it has radius 1, that represents the boundary of stability for difference equations. So if you're in that circle, you're stable. If just one root of your system is outside, the whole system is unstable. Oh, okay, I see what you're saying. Magnitude less than 1. Well, I guess... No, because magnitude can't be negativo. Yeah, magnitude's an absolute value. Okay. Let's talk about oscillatory difference equations. And first, we're just going to take this one, a second order difference equation, and absolute value of z greater than or equal to 0. The value I got in the homework was negative, but less than 1. Well, the magnitude, let's calculate magnitude really quick. Like, actually, we'll get to that. We'll get to that on the second page. Wouldn't it be less than or equal to 1? Well, if it's equal to 1, I wouldn't call it stable, because the response will never decay. Like, it would be like if it was this rabbit population model, if the magnitude of the root was 1, it would just like stay at this stage forever. You could call it critically stable, marginally stable. But in real life, rarely, or I mean, if ever, do you find anything that just stays exactly where it is. It either decays or grows. All right. Let's go straight into some MATLAB, because I want to show you how to simulate this in a for loop. This is what I call a recursive solution. All right, I'm just opening up a new MATLAB window. Meerkat says, how does stability affect systems? If a system is unstable, generally in real life it means it's going to break. So this is the method for part 3 on the homework. Yes, what I'm showing you right here corresponds to part 3 in the homework. So let us say, so we'll just call this like recursive. Oh, I can't spell recursive. Difference equation. So the first thing we're going to do, we're going to talk about like the number of steps that we're going to simulate. I think in the homework we do 20 steps. So number of steps in the simulation. And Let's say x is our dependent variable. Let's say x is our dependent variable. When we have imaginary roots and use sine and cosine, do we consider radians or degrees? Typically radians. So let's initialize this vector. The way I like to do this is to make a column vector, and its length is n. So it has 20 spaces in it. Usually MATLAB is happier with you if before you start filling in a variable iteratively, you tell it in advance how many spaces this variable has. So this is just initializing the x vector. So this is our dependent variable. We're going to be updating it. And now we're going to give initial conditions. One thing to note about indices in MATLAB, check line 3. So what are you talking about? The indices in MATLAB start at 1. In Python, they start at 0. Probably in C++, they start at... Oh, it looks like a minus... Okay, here we go. I think the resolution... It's an equal sign. I just have to zoom in a little bit. I know. You were just helping. Okay, so at the 0th index, the dependent variable was set equal to 1. Or wait a second here. What do I want to do? Okay, let's go back here really quick. Because I did something a little different here than I did in the homework. I say that the initial condition at index 0 is 1. And then I say for indices prior to 0, so like if you could go to x minus 1, x minus 2, I'm saying just assume those are 0. All right, so what I'm going to do in MATLAB, let's go back here. I'm going to set x2 equal to 1. And I know this is index 2 in MATLAB, but assume this is where k equals 0. And then x1, the first index, let's say, assume this is... Wait, do I want to do that? Let's try this. Let's try this. This first index, this is a little weird. I forgot about this. But assume that's where k equals minus 1. Those are just my first two initial conditions. And then I'm going to have a loop that's going to go from 3, because we already have 1 and 2. And let's take it all the way up to... Antonio says, I did a matrix with k in the first column and x in the second. Okay, you could do that. You could do that as well. Let's do 3 to n for now. So we're just going to iterate through this. And here's where we're going to use our difference equation. xk is equal to something. So on the sheet, I think it's equal to 1.523 times x at the prior index minus 0.8819 times x, 2 indices prior, 2 time steps prior. let's just start with this, and you'll see, like, this for loop, it's going to go in where k is going to start at 3, and so it's going to say the third index of x is going to be equal to 1.5 times the second index minus the first. You think the equation on the sheet is different? Are you trolling me? Oh, whoops. I think this is right. 1.523. Oh, okay. So this is a little different in a way, because this is saying xk plus 1 equals 1.523 times xk. And so, like, in my for loop, I'm actually defining x at time step k. Okay, how about we actually be consistent with this sheet? Okay, but if I do this, you can see that this is the same equation, though. It would just be shifted one index. And in this case, I would start my loop at 2, because I already have x, 1, and 2, and I need to calculate the third. And so this will calculate up to, I guess, n plus 1, the 21st sample. So maybe I need to go to n minus 1. Because x is only of size 20. And if in the loop I'm calculating x, k plus 1, the last value of k is going to be n minus 1. So n minus 1 plus 1 would be n. Sorry, I didn't mean to make this example as confusing with the indices. I actually think it's more straightforward in the homework. So maybe it's good that we're seeing this little trickier example in lecture. Okay, so this for loop is going to run through. Okay, so next what we need to do is just plot the results. So in the plot command, the first variable is going to be the x-axis. And just for now, I'm going to put k. And then the second variable is going to be your vertical axis, your dependent variable. So I'll just put x for now. I think I'm going to have to update this. And then I'm just going to use dots, black dots. So in MATLAB, k is black. That stands for the color black. And then this will just put a dot. And I'm going to use the command marker size. And this just pumps up the size of the dot that it's going to draw. Okay. And then I'm also going to turn on the grid. Let's run this. And I'll have to save this. Let's save it here. Let's save it here. Let's do recursion example. Wait, do you want all this for the homework too? Well, you're doing something like this in the homework. Oh, these specific settings? No, that's okay. Wait, what did I... Okay, I'm sorry. K is just a scalar right now. Don't plot whatever index you use for the for loop. That's just a number that's going to change with time. I need to instead plot. Maybe I'll just make a new variable. I'll call it k for plotting. Right. I need 1 to n. But actually, I want this. What I put in here for these values, I want these to correspond to the actual indices that I used. So, for example, the first index of this should correspond to the first variable of x. But remember, I'm assuming that this is where the actual index is -1. Couldn't you just write a vector in the loop? I could do that. There's many ways to do it. So I'm going to make this -1 to 18, right? Or is it 19? 18. Okay, perfect. So now I'm going to put k plot. If I could go back, I would probably call this variable k. And I would use a different variable to iterate through this for loop. All right, let's just run this. And you see, we've made this plot at let's put axes labels on here. Let's put some labels. X label. So I'll call this is k. This is the actual index, and the y label is x of k. Let's run this again. Okay. That's a little more clear. K on the horizontal axis, you see that when k is -1, it's equal to 0. When k is equal to 0, we have 1. And then just based on the difference equation, it just continues from there. Now, if I actually wanted the indices to go from 0 up to 20, because actually my index only went to 18 in this case, I actually need 2 more, right? So what I could do is I could pump this up to 22. Maybe I'll just do that. Wait. Oh, then this has to go to, I would have to update this as well. This would have to go up to 20 now. Mine says plot error vectors must be the same length. So when you get an error like that in MATLAB, what that's telling you is that the variables that, like for your horizontal axis and the vertical axis, these are different sizes. Now, if you want to check the size of your variables, you can use the size command or the length command. So kplot, that's my horizontal variable. Its length 22. And then length of x is also 22. So this is, whenever I get that error, this is the first thing I do. I just check the length. If you increase k, the x-axis, a lot, would it settle to 0? It looks like that in the short time, but I'm not sure. Is there a transient steady state response for discrete systems? Yes. Let's pump this up. Let's run this. Because you were asking what happens over a long period of time. How would we pump this up to 2 Hondo? Wait, is that too much? That's okay. And then I have to change this as well. This is bad coding practice. You like, whenever, because I like to change things a lot in my code, this should update with this variable if I change it. Okay, whatever. We're just going to do this. So this is an example of a stable system. Any linear system that is stable will eventually settle to 0. All right. Okay, we'll come back to MATLAB in a second. We'll come back. But I think this is cool to see that a difference equation, which is just based on like some simple rules, like I'm just adding this combination of the 2 prior time steps, it can create these really beautiful looking exponential oscillations. Let's talk about why that is. Okay. Sorry, that example got a little more confusing than I wanted it to be, but hopefully you got something out of it. My apologies. Why is the solution oscillatory? All right. The way we're going to investigate this is we're going to look at a non-recursive solution to this difference equation by using the characteristic equation. Now, okay, these are the steps that you can always take. For a difference equation, here's the general form of the homogeneous solution. X at step k is going to be some constant times lambda to the k. So this would imply that at k plus 1, it would look like this. Or at k minus 1, it would look like this. You would just change that exponent. So we're going to substitute this general form of the homogeneous solution into the original differential equation. So the original differential equation is this. It's xk plus 1 is 1.523 xk minus 0.8819 xk minus 1. So we're going to substitute this in. So I'm going to have on the left-hand side, a times lambda to the k plus 1 is going to be 1.523 times a lambda to the k minus 0.8819 a times lambda to the k minus 1. And we can cancel all the a's out, first of all. You can just divide by that. And I showed you a trick last time. If we want to eliminate the k variable, in this case, we can multiply this equation by lambda to the 1 minus k. And if you multiply every term by lambda to the 1 minus k, you're going to get lambda squared is 1.523 lambda minus 0.8819. So it cancels out all the lambda to the k. And then we tend to write the characteristic equation as some polynomial equal to 0. So we just move everything over to the left-hand side. And then the way that we like to get the roots, I mean, you could use the quadratic formula, but in general, we're going to be dealing with second order, higher order systems, and it's not as easy to do on paper. So we're going to use the roots command in MATLAB. And that's the syntax for it. Why don't we go over to MATLAB and do it? So roots of 1 minus 1.523 and then 0.8819. And so we have a beautiful pair of complex conjugate roots. How do you tell when to multiply by whatever term? Great question, Antonio. So, Brandon also asks unstable. We'll get to that. You know how to check, right? Okay, first, let's look at Antonio's question real quick. So I said lambda 1 minus k, right? So the first term on the left-hand side is lambda k plus 1. If I do times lambda 1 minus k, this is equal to lambda to the k plus 1 plus 1 minus k. So the k's cancel. It's lambda squared. Basically, okay. This is the rule that I choose. I choose to make the lowest power. I try to make the lowest order resulting polynomial that I can. So actually, I look at the lowest order term in the original equation. So I would actually look at the k minus 1 term, and maybe, like, depending on the difference equation, it goes all the way to k minus 3 or something. Anyways, pick the lowest power one. And then what I do is I choose, what do I multiply this with? So question mark makes it equal to lambda to the 0. And that's how I chose it to be 1 minus k. Because I need a plus 1 and I need a minus k. Because that'll, like we showed earlier, it'll cancel everything and it'll be lambda to the 0. So I'm glad you asked that, because that's how I always choose. Can you shorthand this just like with ODEs? Are you talking about getting the characteristic equation? Because you certainly can. I think what you're asking is, just looking at this equation right here, without doing that series of steps that I just did, can you just write down what the characteristic equation right away is? And the answer is yes. Once you've done this a couple times, like, I can look at this and see the characteristic equation will be this. Once you do it a couple times, you'll just see the pattern. And not in space, yes. For any difference equation, you can use the process I just described. And so for now, I'm showing you every detailed step because I want you to understand why this is the characteristic equation. But once we get a couple weeks in, maybe you're already at this point, like, once you go through the homework, you'll see, like, you can write down the characteristic equation really quickly. Okay. Okay. So, we get lambda 1 and 2, this complex conjugate pair, 0.7615, that's the real part, plus or minus 0.5496i. Okay, first question, is this stable or unstable? How about we throw it in the complex plane first? So this circle that I drew, if this is the circle of stability, it'll be plus 1 here, plus I here, minus 1, minus I. Okay, so if we throw the real part in here, 0.7615. So this is 0.2, 0.4, 0.6, 0.8. So 0.76 is, like, kind of close to over here. That's the real part. And the imaginary part is 0.5496. 0.2, 0.4, 0.6. So we're kind of, like, right here. So just playing with it graphically, we are within the circle of stability. This should be a stable system. But how do you explicitly check? Good, we're stable. So the magnitude of each of these roots, so geometrically, it's the distance from the origin. So you can just use the Pythagorean theorem. I don't even know if I said that right. Pythagorean. But the magnitude of the first root is going to be equal to the magnitude of the second root. They're both the same distance from the origin. It's going to be the square root of the real part squared plus the imaginary part squared. So if you were to calculate that, it's 0.9391. Which is less than 1, so, but we already know we're inside the circle. So it's going to be useful to proceed from here to represent the roots in terms of their magnitude and phase angle. Frito says, what if the roots are not complex conjugates? Magnitude less than 1 for stability still applies? Yes. The same criteria for any type of root. All right, so the magnitude we already have. This is how you calculate it. It's the distance from the origin. The phase, let's use this color. When we're talking about phase, we're talking about the angle. Let's take the positive conjugate root. The angle that root makes with respect to the positive real axis. If you draw a ray from the origin through that root. So if a root is real and equal to minus 1.2, for example, it would be unstable, right? Yes, that root would be unstable because it would be over here at minus 1.2, and it's outside the circle. Okay. So let's calculate that phase angle, theta. This would just be the inverse tangent of the imaginary part divided by the real part. And that's 0.6252 radians. And somebody asked earlier, are we going to be using radians? Are we going to be using degrees? Radians. We will use radians. It's always safer. Okay, now I want to express my roots in terms of the magnitude and phase. Danny says, does the magnitude of these roots relate to the speed of the system, similar to how the root is more negative in a differential equation results in a faster settling time? Yes, precisely. So we're going to talk about this especially on Friday. But the closer that the root is to the origin, meaning that the smaller the magnitude is, the faster the system is in terms of it'll take less steps to decay towards zero. The closer the root is to the boundary of this stability, the slower it is in terms of the number of steps it takes. Now, I won't talk about this too much now, but that doesn't mean in real life the system is faster or slower, because this depends on your sampling rate. Like, for example, you could have a system that is, let's say it's fast, like it quickly decays to zero in real life if I'm just watching it. But maybe I'm taking measurements from that system at like 1,000,000 times a second, like a megahertz sampling rate. So even though that system might be fast, I take 1,000,000 measurements before it even has a chance to move very much. So the root for that system, for that sampling rate, it might appear like a slow root, like maybe it's very close to the boundary. But that just means that it takes many sampling steps to decay. That doesn't necessarily mean it's fast or slow. Okay. Let's write these roots in terms of magnitude and phase. So we know what these roots are, what the numbers are. The real part will be the magnitude of the root, let's just call it 0.94, times cosine of the phase angle. So let's just call it like 0.63. So this is the real part of the root. And then the imaginary part of the root is the magnitude, 0.94, times sine, 0.63, and then we put an I there. Does anyone else hear music? Yeah, it's a subtle background music. Okay, so we have roots in terms of magnitude and phase now. And I want to write these in terms of a complex exponential next. It may not seem so clear why we want to do this right now, because usually you want to avoid complex exponentials in terms of just representing stuff. But we're going to do that first. So this is 0.94 times cosine 0.63 plus I times sine 0.63. And so the roots are... You appreciate the background music? Okay, great. You're going to have 0.94 e to the 0.63 I. That's going to be the positive conjugate root. So this is using the Euler identity. And the negative conjugate root is going to be 0.94 e to the minus 0.63 I. Okay, so don't get confused here. All that happened is we calculated our two roots, and I'm just writing these two roots in terms of magnitude and phase. Because somebody asked about phase, what does that tell us? Well, you'll see in a second. I'm not going to give it away. But magnitude and phase have physical significance, and so that's why I want to write the roots in terms of those quantities. And it'll become important later. Okay, so we'll call this lambda 1 and we'll call this lambda 2. So now we're going to substitute these roots into the general form of the homogeneous solution, which is the same. It's always the same for difference equations. This is going to be x k at step k. It's going to be a times lambda 1 to the k. Well, let's say a1 plus... Sorry, that looks a little sloppy. a1 times lambda 1 to the k plus a2 times lambda 2 to the k. And if you had 3 roots or 4 roots, we don't have any more in this case, but on the homework, the last problem has 3 roots. And so the way that you deal with it is you would just add a third term for that third root. So just keep that in mind. Okay. We're gonna keep working on this. So this is gonna be a1. I don't know what it is yet, and let's substitute in lambda 1. 0.94 e to the 0.63 I to the k. So that's lambda 1. a2 times 0.94 e to the minus 0.63 I to the k. We were originally finding xk plus 1. Does that no longer make a difference? No, it doesn't, because you could always shift this. So what I mean is, this relationship would also hold if instead I did this, or if I made it k plus 2, or whatever, because k just represents an arbitrary time step anyways. That's a great question, though. Okay, so what I'm going to do is I'm going to pull out this 0.94 term, and it's going to be to the kth power because it's within that parentheses up there. So I'm going to have 0.94 to the k, which holds for both of those terms, times a1 e to the 0.63k I plus a2 e to the minus 0.63k I. All right, so we just pulled out the 0.94 to the k from both terms, and then we took that exponential term to the kth power, which just, it multiplies that exponent by k. Now we're going to use Euler's identity again, and we're going to write these complex exponentials in terms of sines and cosines again. And looking at the clock, I know we're at 1:30. Give me 4-5 more minutes, because we're going to get to a final form that's going to help you with your homework, okay? All right, so we're going to have 0.94 to the k. And then I'm going to have a1. I know time flies. I was a little ambitious today, I guess. I thought we were going to blast through. Is this note sheet going to be posted today? I'll post this right after class. Okay, so e to the 0.63k, that's going to be cosine 0.63k plus I times sine 0.63k. So that e term becomes this. And then we can't forget about the other one. A2 cosine 0.63k, but this one is minus I sine 0.63k. When you have a negative complex exponential, you have to subtract that sign. And then we got to close off this big bracket. Maybe we'll make it a square, so that's a little more clear. Now, this is a little bit, it has some complex terms in it. It's a little bit nasty. These terms, A1 and A2, it turns out that these also must be complex numbers. So what I mean is A1 is like C1 plus C2 times I, and A2 is like C3 plus C4 times I. It turns out if you want this difference equation to have a real solution, like when we plotted what the solution looks like earlier, right? It's a sinusoid and it's real numbers. Anyways, for this to be real, those have to be complex. There are additional manipulations you can do, and I'm going to post those notes for you as well. But this goes into an alternative form with different coefficients. I'll call these A1 hat and A2 hat. This A1 hat is a real number. It's different than A1 up above. It's totally unrelated. A2 hat sine 0.63. Okay. So these two are just nice real numbers. And this is our expression for xk. So this is the explicit solution for this difference equation. It's not in terms of prior time steps. I'll just make a note here. If I wanted xk plus 1, I could just make all of these k plus 1 in here. It holds for any value. And if I want to solve for A1 and A2, you use the initial conditions of the problem. All right. So let's just do that really quick to bring this full circle. So I said x at time step 0 is equal to 1. So let's just assume we were just using k here. So this means k equals 0. I'm going to have 0.94 to the 0. A1 hat times cosine 0 plus A2 hat sine 0. So this would be 1 times A1 hat plus A2 times 0, because sine of 0 is 0. So from this initial condition, we're going to have A1 hat equals 1. On the homework, should we be writing complex roots in terms of magnitude and phase rather than real and imaginary parts initially found from the roots example? No, it's fine. It's fine. You can give the roots just as the real and imaginary parts. What you need to know is when you're solving for the explicit solution, the easiest way to do it is to use this sine and cosine form. And that uses the magnitude and phase. In my opinion, that's the easiest way to write the explicit expression and to solve for any unknown coefficients that are based on the initial conditions. Excuse me. Okay, let's use another. Benny says, I know we're out of time, but can we quickly do the MATLAB after we finish the handwork? Maybe I'll do that, because if you have to go, that's okay, because the video is going to be posted. The video is going to be posted right after, so you can always come back to this. The videos are, if you go to the videos link on my Twitch TV page. So I know we're running over a little bit today. My apologies. My apologies. We weren't as tight today. Okay, let's do the next initial condition. Now, when you use initial conditions, forget that. So this one was 0. So I'm going to have 0.94 to the minus 1. A1 cosine 0.63 times minus 1 plus A2 hat sine 0.63 times minus 1. Oh shoot, I blocked the links. Thanks for posting that link, Mike. I'll shoot that in the chat later as well. All right. And so for this equation, we already know A1 is equal to 1. So I'll just plug in a 1 there. Okay. So... and actually it's 0 on this side, so I can just divide both sides by this term. And so I will have, if I move this term over to the left-hand side, I'll have negative cosine of negative 0.63 is equal to A2 hat times sine minus 0.63. So A2 hat should be minus cosine minus 0.63 over sine minus 0.63. I'm going to start writing this out in MATLAB over here as you write it down yourself. Minus cosine minus 0.63 divided by sine minus 0.63. This is our A2 term. 1.375. 1.375. Let's go back here. Whew. Okay. Okay. So A1 is 1, A2 is 1.375. Okay, 3715. Oh, thank you guys. Thank you. 3715. All right. Now, what I want to do next. So this is an expression for xk. It should match the result that we got earlier. It's the same differential equation. It's just a different way of solving it. All right, let's go to MATLAB. Let's go over here. So down here, non-recursive solution. Or maybe I should just, it's just like the explicit solution. All right. So just following the template I have in the notes, what I like to do is have the magnitude of the root, which, what was that? 0.9391. And then the, what do I call it? I'll just call it short for angle. And I know that looks like a minus sign, but that's just the resolution. It's an equal sign. That was 0.6252 radians. And then we have our unknown coefficients that we solved for using the initial conditions. A1 was 1. A2 was 1.3715. And next, well, for K, like up above, we use the variable K plot to actually represent the K index. And you know what? Like at this point, this variable is very annoying to me that it's different than the counter. So what I'm going to do, I'm going to change this. No, let's not use I. Let's use, no, it's fine. We'll use I. I'll use something different than K. Then I'll just call this one K. Yeah, that makes me happier with my life. And then we're just going to use this variable K. Isn't I a predefined variable? I think if you have one I, like with no space, like this is predefined. But I think I is okay to use. Okay, so we're going to call x2 our explicit solution for x that we're going to compare. So the general form was the magnitude of the root to the kth power. I think you also need to change k plot to k in your plot. Oh, thank you very much. Up here on line 15. Thank you guys. Now you're gonna have to do this dot. Let's zoom in a little bit. You're gonna have to do this dot caret because we're not taking the power of a scalar. We're raising to the power of a vector. So you just have to notate it this way. And you know what? Maybe we'll throw like some extra parentheses around this to be real safe and insulate it. Okay, and then this needs to multiply by A1 times cosine of the angle times K plus A2 times sine of that angle times K. And people were asking earlier, what's the significance of the angle? Well, this here tells you the significance because the term inside of the cosine is the frequency. So the larger this term, the larger the frequency of oscillation is. Okay, let's see. And this is element-wise multiplication here as well. So you need this dot times. Isn't it angle? Okay, this one you don't need the dot times here because K is a vector, but this angle variable is a scalar. So if you have a scalar doing element-wise multiplication with a vector, you don't need the dot times. You could put it here, but you don't need it. It's only when you're doing element-wise multiplication with a vector and another vector, because this over here is going to make a vector. This over here makes a vector. So we have two vectors being element-wise multiplied. Okay, here's the moment of truth. We have to compare this to what we had before. I mean, I'm a little nervous because it's just felt a little scattered for me today. Okay, what I'm gonna do, I'm gonna take my original stuff and I'm gonna plot a red circle. This is what I like to do. And then this other one, I'm gonna plot with a black dot. And if they're the same thing, then when I plot this, the black dot should land inside the red circle. Okay, let's pump up that marker size again so it's easier to see. And at the top of the code, I like to put clear all, close all. That resets your variables. It closes any previous figures. Sometimes you can run into errors, especially if you redefine variables and then run your code again. So I do that to be safe. Okay, let's run it. Hopefully there's no errors. Ooh, this looks promising to me. Oh, buddy, 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 buddy. So, this is what you want to see on your homework. This is a way to check if your answers are correct. Because that recursive solution with the for loop should give you the same result as that explicit solution with the with whatever. Okay. Okay. So this is the result we wanted. Let's go back here really quick. Okay, like just a quick recap. So whenever you're getting these explicit solutions, your first step is to come up with the characteristic equation. However you want to do that. So this was a second order system. We got the characteristic equation. Then you want to find the roots. The type of roots that you get, that's going to dictate the general form of the explicit solution. So the solution is always going to be of a form like this. However, if you have complex roots, what I would suggest is you immediately go to a form like this. And this is so messy at this point, but like if you have a pair of complex roots, the general form of the solution is you take the magnitude of those roots to the kth power, whatever that is, and then you're going to have one term, and I called it A1 hat earlier. It's a real number. You're going to have that phase angle in radians times k, and then you're going to have A2 sine that phase angle times k. And then to get these, use the provided initial conditions of the problem, like xk is equal to something, x2, x3, whatever. It doesn't matter. You can use any two steps. One last thing that I want to say. For the very last problem of the homework, you have a system that has three roots. When you're writing out the general form of the solution, remember I said xk is going to be like a1 lambda 1 to the k plus a2 lambda 2 to the k plus a3 lambda 3 to the k, and like so on and so forth. So if you have, so you might have some complex roots in there, you might have some real roots. If you have complex roots, you just take this part, and then if you have like real roots after that, you might have like A3 times, I don't know, whatever your third root is to the K, and so on like that. D Stratus, I did my calculations in MATLAB and not by hand, but wrote some of the steps out. I got my unknowns A1 and A2 in real and imaginary parts. My graphs matched. Is that okay? Oh, right. You could write this. Let's see. Because, I guess, like, you could, like, this is a valid form of the homogeneous solution, And you could solve for these complex coefficients, and I think you could get the graph to match, but it's not a standard way of doing it, because the solution should be, in the end, you want to write your solution in terms of real coefficients. If the system is unstable, then also the solution should match. Yes, it'll still match. Do you want us to derive this in the homework, or can we skip straight to that form? It's okay if you skip straight to a form like this. That's fine with me. How do you know which is cosine and which is sine? It doesn't. I mean, this right here is just a general form. Like, you could throw. You're just gonna have something times the cosine and something times the sine. Like, I could have called these arbitrarily A1 and A2, like switched it. D Stratus and, oh yeah, that guy who stinks. This is related. I might be wrong, but I think that's because MATLAB only plots the real part. Anyways, yeah, when you do a plot, MATLAB will only preserve the real part. But I think you'll find that your imaginary part will go to 0 anyways. Should we show all the steps in the notes in the homework? It's okay if you use this form or whatever, but you should always err on the side of showing more work. It's always better to show all your steps. You don't want to leave out steps. Okay. I know we went long today. I was a little scatterbrained. We'll try to keep it generally tight to 50 minutes. That's my goal. But we might have, sometimes this might happen where we go a little longer. So I appreciate you guys being patient. And if you ever have to go, feel free to do that. You can come back to the video. Ashish says, can you please explain again the last question, the extra thing we need to do if it has 3 roots? Well, like, okay, like I'll give you an example. This is the nice thing about linear systems. Let's say I have a system with 7 roots. And yeah, we'll just do this. And like, I have 2 pairs of complex conjugate roots. So this would be like a 4th order system up to this point. Let's just make it 5th order actually. And the 5th root, let's just say the 5th root is just a real number. What you can do for each of these complex roots, you can calculate the magnitude and the phase. So maybe we'll just call this like mag 1, angle 1. And for this one, it has its own magnitude and its own phase. The general form of the solution for this 5th order system is you would just add up the general forms of all the contributing parts. So like from lambda 1 and 2, you're going to have something like this. This is the general form for complex roots. You're going to have mag 1 to the k. and we'll call it like A1 cosine angle 1. And like Benny was asking, like, how do I know which coefficient goes with sine and which goes with cosine? It doesn't matter. You'll just have some coefficient in front, whatever you want to call it. And then when you use the initial conditions to solve for those coefficients, it'll all work out. So this is for my second set of complex conjugate roots. So I'll have cosine of whatever that angle was, and the sine for whatever that angle was. Oh wait, this should have been angle 1 up here, because it's from that first pair of roots. And then for our fifth root, the general form is just if you have a real root, the general form is just a constant times that root, or that root, whatever that root was, A5, I guess that's what I called it. It's just some number, A5 to the K. And so this is the principle of superposition. It just makes it very nice to write a general form of solutions. This would be true if you had like 20 roots. Some of them are complex, some of them are real. Like if I had another root that was real, like this was 6th order, then I would just add that extra piece, A6 to the K. Flight dynamics student says, so for cosine and sine, the coefficients don't matter since you haven't solved for them yet. Yes, that's what I'm trying to say. At this point, these just represent coefficients that I don't know yet. So I could call them any variable that I want. You know, I've just chosen to call them like A1 hat. You might call them like C1, C2, C3. They're just unknown coefficients. We haven't solved for them yet. Now, if this is a 6th order system, how do I get all of these? You're going to use 6 initial conditions. And it doesn't matter at which step you get those conditions. It could be like 0, 1, maybe they give 3, 5, 7, 8. You just need 6 different measurements of this system. But usually you get like a sequence at the beginning, and those are your initial conditions. That guy who stinks, you're welcome. See you on Friday. Yeah, if you guys have any more questions, don't hesitate to reach out to me or the TA. Use the Discord as well. People are being super helpful on the Discord. Is the homework due by a certain time on Friday, says Brandon. It's due by 8 p.m. Yeah, thank you, Pika. Hey, you guys are so welcome. It's always my pleasure to help out. Hey, see you, Belcut. I know this is kind of a lot at once. It's a little confusing. We'll answer your questions. Keep at it. You're very welcome. Thank you, guys. Whew. Speed chess? Flight says, only class I don't mind running overtime for. Hey, glad you enjoy it. Go Zags. Where's the link to the Discord again? Go check out our syllabus on UB Learns. You can find the link there. Do I have any pets? No. But I love dogs. Okay, we're gonna do a chess match. Turns with zeros, maybe a now playing ticker somewhere in the overlay. I recognize several of the songs and couldn't place them. That's a great idea. Okay, the only thing about that is I'm using a UB computer that I brought to my home. And I don't have administrative access. So, like, if I have to install any apps, I have to email UB IT, and I would have to tell them, like, hey, can you install Pokemon Go on my desktop? And they'll be like, why? Can you install a song ticker? Could you stream? Oh, I should stream Animal Crossing. Not a bad idea. In fact, it's an excellent idea. Okay, who's playing me in chess? Brandon? You got to look up Dr. Estes on chess.com. If you play, I'll totally come to your island. I actually do have Animal Crossing, and my island is total crap. Everything is still tense. Because Animal Crossing feels like work to me. It feels like work. You have to, like, build this for that person. I have to pick all the weeds. I have to fish. I have to do all... It just feels like a lot of work. You spent 2 hours playing before class? You just redid your island so all your rocks are in one area. You're making an account now? Wait, move all the rocks? Nuka says, I did Workshop 1 and background music is Animal Crossing. Nice. Very tasteful. My wife Hannah made an amazing island. Were you playing against Dr. Lagore based on the completed game section? Yes. He's actually really good. He beats me every time. Okay, let's do a puzzle. I don't know if there's a faster way, but I paved over the whole island except for where I wanted the rocks. I really want to see your island. Wait, what's the correct move for white? I assume I check. And then do I run this pawn down the board? No! Antonio says, would be with Dr. Lagore now, but he had to cancel lecture. Oh, shoot. Okay, probably do... Okay. Let's do another. What's the move for black? What's my username? My username is just Dr. Estes. Not prof. See you later. Thanks for stopping in. Oh my gosh, I'm so hungry. Wait, shoot me a challenge. Do I like jazz? I do enjoy jazz. Like, Blue and Green, right? That Miles Davis album. That's what it's called, right? Oh man, it's so great. you have a good album for me? I'm looking forward to it. Are we doing this, Brandon? What's going on? Did you make a username? Good grief. Ugh. Okay. I need to eat some lunch or I'm gonna die. Thank you guys. See you on Friday. Oh, shoot it to me on Discord. Have a good one, Kate. Have a good one, everybody. Have a good lunch. Yeah, thank you very much. It'll be delightful. You're ready? Now you're ready? Let's play on Friday. I'm so hungry I'm gonna die. All right, see you, everybody.